Okay, so we might as well get started. So we had ended up last time just reviewing some basic thermodynamics. So we had ended up just talking about the conversion between molar-based quantities, and so basically, an overbar indicates that the quantity is basically it's actually per unit mole, and no bar means it is per unit gram or kilogram. And so you can just basically multiply them or divide them by the molecular weight to go back and forth between the two. So now we're just going to consider a a constant pressure reactor. So that is, we have a little reactor here. It may or may not be insulated, and we have an inlet with some reactants coming in at some enthalpy H reactants, and by cap H, I mean it is the total enthalpy coming in. And so basically it is small h times mass, or small h times density, whichever. And then coming out the backside of it, we have some products that some products that are coming out, and the temperature may or may not be the temperature at the inlet Ti, but it's a constant pressure reactor. So basically, the pressure coming in is the same as the pressure coming out. And so this could be this could be a gas turbine combustor, something like that. And so we just want to consider just do a sort of rough control volume analysis. So we're going to just apply the first law to our control volume here. And we just note that we have a chemical reaction here. So the overall chemical reaction is just basically this here. It's the same thing. It's the sum of nu I prime times species I going to sum of nu I double prime of species I. Okay, so it's the same one that I've done before, and we can just do a first law energy balance, assuming steady state, steady flow conditions. I'm not going to go through that, but we find that the heat, if we want to basically, if we want to do this, the sort of special condition that the products exit the combustor at the same temperature as the reactants, as which the reactants came in, we are going to have to either add or remove some heat. So essentially then what we can do is we can do a first law energy balance, and you can show that that amount of heat coming in is just simply equal to the amount of enthalpy going out minus the amount of enthalpy coming in. So there shouldn't be any shockers here. Okay. And now the heat of reaction, if you consider this, if we made this reactor very well insulated, you would find that intuitively, after you burn, say, methane and oxygen, the exit temperature would be extremely high. And so if we instead remove heat and remove enough heat such that this exit temperature is equal to the inlet temperature, and then find that amount of heat, that's called the heat of reaction. And so you could consider that heat of reaction is the amount of chemical energy that is liberated by a chemical reaction. Okay. And often you typically assume that heats of reaction are at 25 degrees Celsius or 298.15 Kelvin. And this is often, written like this. And because if we go back up to here, we have this change of sensible enthalpy. And the sensible enthalpy, if I scroll up a little bit, is basically just this integral here. Okay, except for its CP, because it is the enthalpy, or the change of sensible enthalpy. So, and the reference temperature for that is 298.15. So if Ti is at 298.15, there is these changes in the sensible enthalpies are zero for both the products and the reactants. So in that special case, we can define the heat of reaction as just QP under the condition that the temperature of both the reactants and the products is at 298 Kelvin or 298.15 Kelvin. Okay, and so the change of the sensible enthalpy goes away, and the only thing we are left with is just the sum of the stoichiometric coefficients for the reactions, or for the reactants and products, times the enthalpy of formation, which again, the enthalpy of formation just accounts for all the chemical bonding energy. Okay, and you sometimes see these written separately for a chemical reaction, and sometimes you can look in some references and see that the heats of reaction are actually written in the reaction string itself. So this is a paper on modeling aluminum combustion that I've used in the past. And they write their aluminum reactions like this. So you have Al plus 3/4 O2 goes to 1/2 Al2O3 minus 8.103 times 10 to the 8 joules per kmol aluminum. This little minus 8.103 times 10 to the 8 joules per kmol, that is the heat of reaction. Okay, so you do sometimes see that, and you do need to pay attention to the units, especially in terms of what it's it's per kmol of. So like sometimes it might be per kmol of O2. It is normally traditionally they write when they write the reaction in this format. The heat they basically normalize it so that you have 1 mole of fuel. Okay, but still pay attention to it, the kmol, and also what species it's a kmol of. And if there's no species listed, then it is understood to be for 1 kmol of the fuel. Okay, so pay attention to those units. And an exothermic reaction is indicated if you have a negative heat of reaction. And this seems a bit counterintuitive, but if you think about it, what a negative heat of reaction means in this sort of reactor here, it means that QP is leaving the reactor, and we define QP to be positive going in. So basically, all the negative heat of reaction means is that to maintain constant temperature, you need to remove heat from the reactor. And that indicates an exothermic reaction. An endothermic reaction is the exact opposite. That could be a sort of reaction such as, say, splitting hydrogen into, splitting H2 into 2H, or O2 into 2O, things like that, or H2O into H2 plus O. Those are all endothermic reactions. And so to maintain constant temperature, you're going to have to add heat to the system. And there is a special case of the heat of reaction that is used quite a bit. That's called the heat of combustion. And that's simply equal to the heat of reaction when the products are assumed to be at complete combustion and the reactants are stoichiometrically mixed. Okay, so the heat of reaction is for any random reaction. The heat of combustion is for the very special case that the products are at complete combustion and the reactants are stoichiometrically mixed. And you find this parameter quite often for a lot of fuels because it's very easily, it has a nice, easy definition. It's not based off of how you do the reactions or how you define the chemical reactions or anything like that. And the heat of combustion is definable for explosives. And commonly, you need to make an assumption as to what phase the H2O in the products will be. You can assume that it'll be in the gas or the liquid state. Strictly speaking, from a strict definition standpoint, you should use the liquid state. But from a practical standpoint, that's not really characteristic of the useful energy that you're going to get out of a chemical reaction, because that would imply that coming out of the reactor, you're going to have liquid droplets coming out, and all the energy that is liberated with the condensation of those liquid droplets is going to provide useful work. Typically, that's not the case because that condensation takes a very long time for instance, in your car engine, the fact that the water vapor goes out the exhaust and eventually becomes water droplets and clouds in the upper atmosphere does not tell you anything about the performance of your car engine. So I personally tend to like to use the, I personally like to assume that the water vapor is in the gas phase, but Cooper and for a lot of the explosive literature basically assume that it is at the liquid state. Okay, so if you're doing this for an explosive, assume the liquid state, even though I don't think it's really physical, but it's just the way it is. So for example, we just want to find the heat of combustion for TNT. So first we need to find the stoichiometric reaction. Remember, TNT has a very large and negative oxygen balance. So to completely oxidize it, we're going to have to add some O2 or add some air to it. And so if you add some air to it, if you assume complete combustion, that means all the carbon atoms burn with oxygen to produce CO2, and all the hydrogen atoms burn with oxygen to produce H2O. Then you find that you're going to need 5.25 moles of O2 that are needed to balance everything out. So then the heat of combustion is just the heat of reaction for this chemical reaction. So we just basically stick in, we apply this definition. So nu I double prime minus nu I prime for carbon dioxide. We have 7 on the product side and 0 on the reactant side. So it's basically 7 times that enthalpy of formation and so forth for H2O and N2 and O2 and also TNT. And if you substitute in the enthalpies of formation, you get that the heat of combustion for TNT is minus 813.2 kcals per mole of TNT. Okay, so it's pretty straightforward. It's just a matter of basically looking up. Really, the hardest part about solving these types of problems is often for some of the exotic materials, finding the enthalpies of formation. Okay. And so here's just some common heats of combustion for a lot of traditional hydrocarbons. Okay, so I'll scroll here. Now, for an explosive or for traditional hydrocarbon, you typically only need the heat of combustion. But for an energetic material that can burn by themselves without additional oxidizer, we would like to characterize that amount of energy that is liberated while that process, if it burns by itself. And for an explosive, that's called the heat of detonation. And for a propellant that just burns, that's called the heat of explosion. And these are both really the same thing. And it's the chemical energy that is released from the detonation of an explosive or the burning of a propellant. And empirically, because when we cover flames and detonations, you will realize that the products are at different states, massively different states for a detonation and the propellant combustion. And because the species compositions are different, the heats of explosion and detonation are different. But if you assume that the product composition is the same for both the flame and the detonation, then they will give the exact same units. Okay, but in general, they are different, and that is only due to the different thermodynamic states that are produced by a detonation or a burning propellant. Okay, and then typically you would just sort of look these up, and if data are not available and you need to make an estimate, you can use the Kistiakowski-Wilson rules to basically estimate. And now since there are multiple rules for oxidation of an explosive or of a propellant, you will get different values for the heat of detonation depending on what oxidation rule or oxidation hierarchy or priority that you assume for the energetic material. Okay, so for example, I'm going to use TNT, and again, this is, and we're going to find the heat of detonation basically for that. And to estimate the product state, we're just going to use the modified Kistiakowski-Wilson rules. And so I've already done that, I think. But if you do that, you find it's going to produce first all the hydrogens are burned, so you produce 2.5 moles of H2O. Then all the remaining oxygen consumes carbon, and there's still some carbon left over, so there's 3.5 moles of carbon, and that's assumed to be in the graphite phase, which is just your typical soot particle, and there's 1.5 moles of N2. And so if you find the heat of reaction for this, you indeed find the heat of detonation. So if you go through the same process that we did here for the heat of combustion for TNT, you will find the heat of detonation, and you'll find that is negative 272.2 kcals per mole. Okay.
Professor, can I ask a question about this?
Yeah.
So do we assume that the products are at the same temperature then for these calculations?
Yes.
But in actuality, they're a lot hotter, aren't they?
Yes, they are. But basically, what we are trying to define is the amount of chemical energy that is liberated by the chemical reaction itself. And so you bring the products back down to their initial temperature to basically subtract out the effect of just subtract out the change of sensible enthalpy basically from it. So we're basically trying to separate out the effect of chemical energy from just the normal heating of the gas. Do you see what I mean?
Yeah, I think I see what you mean. So we may have to be careful about this if we weren't in a constant pressure, or I guess if we were in a room or a smaller volume that was confined, and the time scales for which they would return to temperature would be different, or.
Well, here we are really just characterizing the chemical reaction itself. We're not saying anything about the detonation or blast process. So basically what we're saying, if you have a small room or a big room and you detonate some TNT, this is the amount of energy that will be added to the gas by the detonation, regardless of if the room is small or big, or if there's heat loss to the room, sort of things like that. This will be the heat that is added to the room by the detonation of the TNT charge. And so that's why they define the products to be at the standard temperature, to basically eliminate any effects due to changes of the sensible enthalpy of the different species. So that it is only the differences, if you go back up to here, that it is only that it only involves the enthalpy of formation, and that's it. Okay?
Okay, yeah, that makes sense.
Okay. Any other questions? Okay. So you can look at the heat of detonation from Cooper. There's a table of them, and so yeah, and there's there's a whole wide range of them, and also they estimate this is the experimental heat of detonation, where they use a bomb calorimeter, and here are the heats of detonation using two product hierarchies. Here they use the standard Kistiakowski-Wilson rule, and here they use one of the modified ones. There are multiple modified ones, and you can see that based on your product assumption, you can get massively different numbers. Okay, and so that's just something to be aware of. And so if you have access to experimental data for heats of detonation, please use those numbers. because at best, if you have to estimate it, it's at best the back of the envelope type calculation. Okay, and there's also something called the heat of afterburn. You may have noticed that there's a lot of leftover unburned fuel in TNT, and so if you have a stick of if you have a stick of TNT, and we are looking at a detonation that is propagating through it, and so here we have just the raw stick of TNT. We have a detonation wave going through it, and for now, for all intents and purposes, just consider that this detonation wave is instantly converting the TNT to the detonation products, and those detonation products were the 2.5 H2O, the 3.5 CO, and the 3.5 carbon. Okay, so this region here is extremely fuel rich, and it's also at an extremely high pressure, and that extremely high pressure is going to transmit an air shock, and at some point you're going to have a boundary, which is basically roughly right here, a boundary between the shock heated air and these high temperature detonation products, which are very fuel rich. So you can imagine what's going to happen at this very boundary is the air and those detonation products are basically going to mix. And if the detonation products are fuel rich, they can burn again and then basically mix with the air. And that process is called afterburning. And so if you want to see afterburning, this is just a little test we've been doing with our code. Here we have a goofy shaped TNT charge. And the only thing I basically want you to see from this movie, aside from it looks kind of neat, is the flame, which will be in orange after I detonate it. So we have the the detonation propagating out. This here is the blast that is produced. And this region here is just the shock heated air. This region here are the very fuel rich TNT products. And this orange line here is basically the edge of the fireball. And so basically this here are the products of where the air and the TNT products have burned. And so basically that is the fireball. And so for very fuel rich explosives like say TNT, the post detonation combustion processes that are occurring in the fireball are responsible for a huge fraction of the amount of energy released, and that amount of energy release is called the heat of afterburning. And basically, you can show is that basically you consider the heat of reaction starting from the products of starting from the detonation products, and you add enough air to basically burn it completely. And you can show that mathematically that the heat of afterburning is just simply the heat of combustion, which considers the whole process from start to finish, and you just subtract off the heat of detonation. And so, or you can start from just the burning of the detonation products itself. Either way, you get the exact same number. And so you find that the heat of afterburning is 565.9 kcals per mole. And so we find that the heat of afterburning for TNT is higher than the heat of detonation. Okay, and I do need to fix a sign error here. Okay, so are there any questions with that? Okay. Now, one other concept that we'll go over a little bit, not too much, would be the adiabatic flame temperature. Now, we had that constant pressure reactor, and we defined, and for the heat of reaction, we defined there's a heat release such that you maintain constant temperature. what if instead we make that we make it very well insulated so that there's no heat lost? And so basically we'll call that temperature the adiabatic flame temperature. And you can do a first law energy balance, and it would be pretty straightforward to show that the enthalpy of at steady state conditions, that the enthalpy of the reactants is the same as the enthalpy of the products. So now this for those of you who this is your first time with combustion, intuitively, if I have hydrogen and oxygen coming in here, and this is a burner, you expect the temperature to be extremely high, and so, but yet the enthalpies are the same. So how can that be? Well, remember that the enthalpy includes both the sensible enthalpy, which is the one you normally think of, and also the enthalpy of formation or the chemical energy. And so if you look at so the answer to that question is, how can the temperature go up if the enthalpy stays the same? Is that the chemical reaction is changing the partition between chemical energy and sensible enthalpy. By sensible enthalpy, it's often called that because it is the enthalpy that you can sort of quote unquote sense with a thermocouple. And if the total energy, which is the sum of the chemical energy and the sensible enthalpy, if that needs to be sort of constant, and if the temperature is going to increase intuitively by the chemical reaction, then that means the sensible enthalpy has gone up. So if the sensible enthalpy goes up, that means the amount of chemical energy has to go down. Okay, so basically this implies that the products have lower chemical potential energy, which means that to keep the energy constant, the sensible energy increases. So if you look at this, it's sometimes called a Le Chatelier diagram. We just plot the enthalpy as a function of temperature for the pure reactant state and the pure product state. And so notice that if we have the adiabatic flame temperature, it's a constant enthalpy process when we go from the reactants to the products. And if the enthalpy of formation of the products is lower than that of the reactants, we basically take this curve here and basically shift it down. But for the flame temperature, it's a constant enthalpy process. So that means we basically slide to the right at constant enthalpy, and that temperature where we land on the products is the adiabatic flame temperature. And also just a note that if we basically impose constant temperature conditions and we start at the reactants and we go down to the products, that is our heat of reaction or QP. Okay, and so even though the enthalpy is constant, it does not mean that the sensible enthalpy is constant. So when we're dealing with combustion, there are multiple forms of energy that we need to consider. So are there any questions on this? And that's all I'll talk about the adiabatic flame temperature for now. Okay, so on to part 4. Okay, so up to now, move that out of the way. So up to now, we have been dealing with ideal gases. So in this class, since a lot of the pressures we deal with are extremely high, we need to discuss some stuff about real gases. And so we will introduce some thermodynamics of real gases. And so I will introduce them. And for those of you who've had some advanced thermodynamics, some of this will be review, and we'll describe some of the equation of state models that are commonly used. Have to discuss briefly Maxwell's relations, and then departure functions. Okay. So equation of state, I'll call those EOS models, and we call them models because, at least from the high explosive world, they are often empirical models, and every strict sense of the word. And so really, it's just an equation of state relates pressure, temperature, density, and also the mixture composition, either in terms of mass fraction or mole fraction, or number of moles of species I, things like that. Okay, so it's just some function. And there are a wide variety of these models that are used in combustion, ideal gas, Peng Robinson for like supercritical stuff, all sorts of equation of state. Benedict Webb Rubin is a very complicated equation of state model, and it is one of the equation of state models that is used to make the thermotables that are in back of your book. Okay, and so I'm going to go over some of these in detail, but not all of them. Okay, so and before I discuss those, we need to discuss the compressibility factor. And so how these real gas equation state are often defined is they are defined using a compressibility factor. And so if you take the ideal gas law, which is just P equals rho RT, they just multiply it by this bogey factor Z. And Z is the compressibility factor. It just accounts for the non-ideal effects. And so clearly for an ideal gas, Z is just defined to be 1. But in general, this compressibility factor is a function of pressure, temperature, density, or volume, same difference, and also the chemical composition. So it's a function of everything in general. Okay, so now we will discuss some basic equations of state. And so probably one of the easiest, aside from ideal gas, it's called the Nobel-Abel equation of state. This is a so-called co-volume equation of state, and this accounts for the volume of the molecules. Whereas ideal gas just did not account for the volume of the molecules. And so the ideal gas equation of state is inaccurate at very high pressures because the molecules are jammed so close to one another that they can actually touch one another. And the ideal gas model, it basically lets them completely overlap. It does not account for that volume. Whereas the Nobel-Abel equation of state, which is a co-volume, it accounts for the volume of all the molecules. It does account for that. And the Nobel-Abel equation of state, you see it used quite often for internal gun ballistics. So if any of you wind up working for the DoD labs or a company that design guns and things like that, you will be using Nobel-Abel for that. And so the Nobel-Abel equation of state is defined to be P times the specific volume, which is defined to be 1 over rho minus B. B is the co-volume, is equal to RT. So it's almost the same as the ideal gas law, except for you just subtract off the volume of the molecules is basically all you do. And rearranging, we can find that P times 1 over rho minus B is equal to RT. And you can basically play with this and find what the function of the compressibility factor is. Okay, and so this is a very simple non-ideal equation of state. It tends to be less accurate at low pressure than the ideal gas model, because this co-volume effect does not disappear. It should actually sort of disappear. And the co-volume is typically a constant, but you do need to look it up for your gas composition. Typically for gun propellant products, which is where it's most commonly used, it's on the order of 0.001 meters cubed per kilogram. Okay, and so that is typically what that is. And when we've used it, when I was working at Penn State, that is right around the number that like we would use. Okay. The other equation of state, and this one you're going to have lots of homework on because it's not too trivial, but it's also not too super duper complicated. And that's the Becker, Kistiakowsky, Wilson, or BKW equation of state. It's really a more sophisticated co-volume equation of state. It easily allows for mixing of different species, and you can account for the different coal volumes of all the different species. It also limits properly to an ideal gas at low pressure, and it is reasonably accurate at explosive pressures. So we can do mixtures, we can do low pressures, and we can do high pressures. And so, here the BKW, it's given by P is equal to basically rho RTZ, and Z is just defined to be 1 plus X e to the beta X, where beta is a constant, and X is defined to be this crazy function here, and and where these K hats are the molar coal volumes for all the species. And so that's the volume per mole. Okay, and this alpha is a constant, theta is a constant, and so there are all sorts of constants with these, and kappa is a constant. But this is basically how it's defined. And here, if we look at the compressibility factor that is produced as a function of volume and temperature divided by 1,000, we see that at very high densities are very small, or at very small specific volumes, we can have compressibility factors in excess of 5 or 6. And so this would be, so basically this range here would be typical of a high explosive detonation type of conditions. And this region here, this big region here, would be an ideal gas region where the compressibility factor goes to almost exactly 1, and it behaves as an ideal gas as it should. Okay, and so you guys will be getting, for your homework, we'll be getting more familiar with this equation state, and I'll have a few examples. Now, for those of you who work not with explosives or really high pressure conditions, but you work with normal combustors or diesel engines, even typical gas turbine combustors, the pressures are starting to get high enough to where you need to consider the vapor dome in your equation of state. And so, supercritical conditions, if you remember, you're on a PV diagram from your thermodynamics, where we have PV, and we have this sort of saturated vapor dome here, where on this side here we have subcooled liquid, and on this side here we have superheated vapor, and in between here we have a mixture region between that contains, basically water droplets or something like that. So it contains a mixture of liquid and vapor. Okay, now the pressures in traditional combustors, the pressures are basically low, to where the fuel is normally in a subcooled liquid state, and the products and the oxidizer are in the superheated vapor state. Now, to increase efficiency, modern combustors are bumping up the pressure higher and higher and higher, and now the pressures are now so high that at least for some of the species, we need to consider the fact that the pressure is so high that they're actually getting close to the critical point, and the critical point is the very top of the vapor dome. And so supercritical conditions are said to occur that if both the temperature and the pressure are basically greater than the critical point. And so basically here we just drew the sort of critical isotherm here. And so in this region here, where it is both higher than the critical pressure and higher than the critical temperature, it's said to be supercritical conditions. And a lot of modern combustors, even diesel engines, operate at least partially in supercritical conditions. And supercritical fluids are really interesting. That is the sort of nice, well-defined interface that you normally think of for a fuel droplet or something like that, or a water droplet that vanishes. So the surface becomes fuzzy. It doesn't have surface tension, and also supercritical fluids, they can have the density of liquid, but the viscosity of a gas, so they behave sort of strangely if you're not too familiar with them. Okay, so for supercritical combustion, where you are worried about the critical point, we need an accurate equation of state that is not too crazy complicated that can replicate some of the features of this critical point and basically nearby it. And one of the classic equation of states that can do that, albeit poorly, would be the van der Waals equation of state. And this is a so-called cubic equation of state model. And that accounts for the cold volume effect and also intermolecular attraction and repulsion forces between all of the molecules. Okay, and so again we have the cold volume effect, and this here, this A, it is related to the intermolecular forces. And if you rearrange this, I'm just did some simplification. We can actually put this into a form of P equals rho RT times a bogey factor, and this bogey factor is just the compressibility factor. And so for say van der Waals, the compressibility factor is just basically this function here. And notice if you set A equal to 0 for say van der Waals, you get no-Bell-Abel. Okay, and in theory, you can relate the constants A and B to basically the temperature Tc at the critical point and the pressure of the critical point, and that's based on basic theory. However, this is a nice van der Waals is a nice illustrative equation of state model, and it's not very accurate. So for practical combustion simulations and in calculations, it's simply not used. What you see used quite often is an equation of state called Peng Robinson. It's also a cubic equation of state. It's substantially more accurate than van der Waals, and that equation of state is given by P equals RU times T over V bar, where again V bar is the molar volume, which is just 1 over the mixture concentration minus this term here, A, divided by this denominator here, where basically W is -1, U is 2, and B, which is obtained through a combination. I'm pretty sure it's semi-empirical. And B is basically given as a function of the gas constant and the critical point, the critical temperature and the critical pressure. And A is also a function of the gas constant, the critical temperature, and the critical pressure. And also another function of omega, and that omega over here is called, and that function is right here, and omega is the eccentric factor. And it's just in the derivation of these, I've only seen it once. And the derivation of these, the physicists, they basically wind up doing a Taylor series expansion, and typically they will only take they'll only take a first term, and the eccentric factor is the coefficient for the second order linear term. Is basically where the eccentric factor comes from. But don't quote me on exactly what term that they did that with. I haven't looked at that derivation in a very long time. Okay, and then also Peng Robinson works well for basically various mixtures and sort of things like that. And so there are much more information on this in the back of Quo's book. And also there's a paper on this that very recent paper that discusses Peng Robinson and some of its modifications. And so here is just a picture from that paper that shows some isotherms as a function of volume and pressure. And so this here is one above the critical point, is an isotherm above the critical temperature. This here is the critical temperature isotherm, and this here is a subcritical isotherm. And so what you can see is that Peng Robinson actually does quite well, and it captures a lot of the critical behavior. And so if you could draw, if I could draw, you would see that there'd be a sort of vapor dome that would be right around here that it actually captures. And it's about 1410 in comparison to real data. It can be off by about 14%, which for a lot of things is an acceptable error. Now, using Peng Robinson, there are some gotchas with it. The fact that it is cubic, and so if you need to invert it to find the volume, you have you have 3 roots to worry about. You have 1 root regions, which are in the superheated vapor region. There is only 1 real root, so it's not too terribly difficult. But if you're subcritical, you can find that for a given pressure and temperature, you have 3 different volumes, say here, here, and here. And there's all sorts of tricks for finding out which one are ones you need. And if you're under and basically finding out if you're under the vapor dome. If you're under the vapor dome, then it gets really complicated. So we're not going to go over that. You just need to be aware of that. Okay, so are there any questions with that? These are the only ones that I will discuss, but there's a lot more of these that are used, and as combustion is being driven to higher and higher pressures, these are becoming more and more important. Okay, so now we know how to relate pressure using these real gas models. Now we need to find out how they influence the internal energy. And so here, just recall the first and second law of thermodynamics. The first law states that the change of energy in a system is equal to the amount of heat going in minus the amount of work going out, where basically E includes the effect of internal energy, small e, plus the kinetic energy, plus the potential energy. So you could just have a control volume. It can be moving, it can be not moving, but that's just the first law for that system. And then the second law, remember that it's just defined such that the change of entropy is equal to the amount of heat going in divided by temperature for a reversible process. That is, it's sort of a very abstract definition, but it's how entropy is actually defined. And so for a closed system, assuming no change in kinetic energy, you can combine the first and second law, and just note that the differential unit of work is equal to PdV. Okay. So now for internal energy, we need to extend the usual ideal gas internal energy to that of a real gas. And really the biggest difference is that the internal energy will no longer be just a function of temperature. It'll be a function of temperature and one other variable. Traditionally for internal energy, you would choose the specific volume to be your second variable. Okay, and so now we need to basically find what this is. We need to work with this, and so we first take the total derivative, assuming that E is a function of temperature and specific volume. So we know that dE is partial E partial T at constant volume times dt plus partial E partial V at constant temperature times dV. This, if you recall, is by definition dE dt at constant volume is the constant volume of specific heat. And that in of itself is a function of temperature and volume. But we need to find this term here. And if we can find this term here, we can actually integrate this to find what the change are we can actually use that to find what the effect of the non-ideal gas behavior is on the internal energy. And so that's where we will start doing on Friday. Are there any questions?
I don't have a question about this specifically, but just as we start going through our homework, if we have questions, are you planning on holding office hours, or would you like us to email you our questions and work something out that way?
Yeah, I can hold. I'll put a poll on Canvas about formal office hours. That